Last class, we discussed inverse trigonometry, and that was doing the unit circle invertedly. That's not the right way to say that, but you get it, okay? I want you to keep that in mind. However, today we are not using inverse trig necessarily to solve these problems. So what I taught you last class about the quadrants that you're allowed to be in for inverse trig, we're leaving alone for a second. What we are doing today is we are solving trigonometric equations and inequalities. Since trigonometric functions are periodic, meaning they repeat themselves, we have infinitely many solutions to an equation if no domain restrictions are given. Today, all day, I'm going to be highlighting domain restrictions in green, just as a heads up. We know from our unit circle that sine of x is equal to 1/2 when x is pi over 6. And also, again, not inverse trig, just like in general, we know it satisfies the equation when we're also at 5 pi over 6. Because sine is positive in quadrant 1 and in quadrant 2. However, since sine is periodic with a period of 2 pi, we also know that sine of x is equal to 1/2 when you're an entire loop beyond pi over 6, which is 13 pi over 6, and an entire loop revolution beyond 5 pi over 6, which is 17 pi over 6. And if we kept looping around and around, having these what are called coterminal angles, we'd find an infinite number of rotations that would give me the same value, because we could go around the unit circle over and over and over and over again with a really, really, really big angle. So what we do instead is we write what's called a general solution for these equations. I forgot what color I'm coloring general solutions for a second. Hold on. Oh, purple. Purple. General solutions for these trigonometric equations. General solutions look kind of funky, but they're actually very easy to write. If I was writing the general solution for the problem we just did, we know that we have a solution to sine of x equal to 1/2 at pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6, and on and on and on. So instead of writing all of those out, we write that the solutions are at x equal to pi over 6 plus 2 pi times k, where k is an integer. Integers are whole positive numbers. So that means we could use the number 1 or 2 or 3 or 4 or 5, which represents the number of revolutions around the circle. We also know that there's a solution at 5 pi over 6 and every revolution after that. So plus 2 pi k, where k is an integer. For cosine of x equal to 1/2, if we think about that, we know cosine of x is equal to 1/2 at the angle measurement of pi over 3, and in quadrant 4 at 5 pi over 3. So we have two equations that represent the general solution, x equal to pi over 3 and every revolution after that, 2 pi k where k is an integer, and 5 pi over 3 in quadrant 4 plus 2 pi k, so every revolution after that. If we do this one more time for tangent, we had to use a different number because tangent is never equal to 1/2 on our unit circle. Tangent of x is equal to 1/2 when x is equal to pi over 4, and at 5 pi over 4 in quadrant 3. But since the period length of tangent is pi, notice this is different, we only have to use one equation to capture all solutions instead of two equations like sine and cosine. And the period changes, so this one is pi over 4 plus pi times k, where k is an integer. So I bet you're probably thinking to yourself, am I going to have to write where k is an integer every single time I answer one of these questions? And the answer is yes. However, mathematicians are lazy, so we've created a set of notations for the phrase k is an integer. So instead of writing where k is an integer, you can write k is an element of the integers. It's not a euro, it is the mathematical symbol for is an element of in set notation. So k is an element of, and then that's the symbol for integers, similar to like the all real numbers, fancy R, you know what I'm talking about? This is the fancy Z for integers. Okay. So let's see what this might look like, and let's practice writing some general solutions. Let's find all solutions to the equation cosine of x equal to negative square root 2 over 2. what I want you guys to think of is not inverse trig necessarily, because we're going beyond just the restricted domains for those functions. Cosine of some angle is equal to negative square root 2 over 2. Can anyone think of the angle that I'd plug into cosine to get negative square root 2 over 2? Okay, I like the over 4s, but since it's negative, what quadrant should we be in? Second and the third. What is the version of pi over 4 in the second and third quadrant? 3 pi over 4 and 5 pi over 4. So these are the two angles that would give me negative square root 2 over 2 around my unit circle. If you're needing help with this because we're still not clear on our unit circle, get your paper plate unit circle out and look around it. That's okay for now. We're learning. Now, if we're wanting all of the solutions, this word all and the fact that there are no domain restrictions, which I will show you what that looks like later, we need to write a general solution. It doesn't just want one or two, it wants literally all of the solutions. So we write two general equations here. We would write x is going to be equal to 3 pi over 4 plus 2 pi k, and x equal to 5 pi over 4 plus 2 pi k, given k is an integer. So this whole thing right here is the solution. The second example asks us to find all solutions to the equation sine of x equal to negative 1. Again, the word all is my key that I want literally all the infinitely many solutions to this equation, and there's no domain restriction, which we haven't seen yet, so you don't know what that looks like. But if I was thinking about this, sine of what angle would be equal to negative 1? 3 pi over 2. That's a vertical displacement of negative 1, so it's the furthest down we go on the unit circle. So is there another place, by the way, where this is going to be equal to negative 1? No, there's only one place around our unit circle for sine, one angle that returns negative 1 for sine. So our equation is x equal to 3 pi over 2 plus 2 pi times k, given k is an integer. All right, example 3. It says find all solutions. Again, our keyword there is all to know we're writing general solutions. Find all solutions to the equation tangent of x equal to 1 over square root 3. Ooh, and this makes me so cringe. What have I not allowed you to do? That. What do you mean by that? Yeah, can't leave a square root in the denominator. So the number we're used to recognizing here is square root 3 over 3. This is the rationalized denominator version of 1 over square root 3. So let's ask ourselves a question. Thinking around our unit circle, tangent of what angle is going to be equal to positive square root 3 over 3? No, yeah, you're right. Pi over 6. Sorry. Where else? 7 pi over 6. Interesting. So if I go to write this equation, here's the deal. I actually only need to write one equation, even though there are two angles that represent this for tangent. The solution would be x equal to pi over 6 plus pi times k, given k is an integer. And let's discuss why, because this is very important. It's tangent, yes, and I told you earlier you only need one, but here's exactly why. Let's say we actually do this math. So I have pi over 6, and I'm going to add just one more pi. Pi times 1. Okay, well, to add fractions, what's the rules of fractions? They have to have the same what? Denominator. So I'd write this as 6 over 6 pi. So what's 1 pi over 6 plus 6 pi over 6? Oh, 7 pi over 6. Isn't that what we wanted to begin with? So we actually are answering with both versions around our unit circle for tangent just by giving 1, because the period of tangent is pi, and it will repeat itself. Make sense? Yes? Okay, but what if I make the equations a little bit more complicated? What if we have to do some solving steps before we get to the idea of the general solution around a unit circle? No fear, I have steps 2. Step number 1 is we are going to isolate the trigonometric function on one side of the equation, if it's a linear trigonometric equation. Then we're going to find the corresponding angle measure on the unit circle. That's what you did just a second ago when you found those angles for me. We're going to have to consider any domain restrictions in the problem. Remember, this is not due to inverse trigonometry necessarily, but due to the actual question, the problem itself. And then write either the solutions or the general solutions, depending on if I'm asking for all or a restricted number of solutions. Example 4 says, what are all the values of theta where 6 times the sine of theta is equal to 3 square root 2? Our keyword here is all, so I'm going to be writing general solutions. There's no domain restriction. But at first glance, we're like not ready to do any sort of trig because the sine is not isolated. Okay, so first thing we need to do is take 6 times the sine of theta equal to 3 square root 2, and we need to isolate the trig part. So if I wanted to get that sine of theta by itself, what do? Divide by 6. So then it says sine of theta is equal to 3 square root 2 divided by 6. Oof, can we reduce that down? 3 over 6 reduces to what? 1/2. So this is square root 2 over 2. Ding, ding, ding. This is the first step. We have isolated the trig function. It got to be by itself. Now I just need to think about what angle measurements give me square root 2 over 2. So sine of some angle is going to be equal to square root 2 over 2. What angle is that? Pi over 4. And then there's another one around our unit circle. Sine of what other angle will be positive square root 2 over 2? The quadrant 2 version of that, which is 3 pi over 4. So we've thought about the corresponding angle measurements that satisfy the given requirements. We don't have any domain restrictions here, so I don't have anything to highlight green, but at this point I can do just like I did at the front page and write the general solutions, which would be x equal to pi over 4 plus 2 pi times k, and x equal to 3 pi over 4, and every revolution after, given k is an integer. Example 5. Let f of x equal to 3 plus 2 cosine of x, and g of x equal to 2. In the xy plane, what are the x coordinates of the points of intersection of the graph of f and g for 0 is less than or equal to theta is less than 2 pi? There's a lot going on here, but it's actually not that hard. There's some things that have changed. Number 1, we now have a domain restriction. We are only going to answer with angles between 0 and 2 pi. That's what that inequality says, between 0 and 2 pi, including 0 but not including 2 pi. And because this question asks me for the intersection of these two graphs, what is an intersection mathematically? Where they cross or where they're equal. So what we can do is we'll say, all right, we're going to solve where f of x is equal to g of x. That would be an intersection point. So f of x is 3 plus 2 times the cosine of x, and g of x is equal to 2. Now, if this was a calculator portion of this test, you'd put f in y1, g in y2, find the intersection when you change the window between 0 and 2 pi. But because I know how the AP test works, this is going to be on the non-calculator FRQ. So don't quit. We have to practice this. But remember, our steps are to isolate the trig function. Think of this as a regular algebra problem. We're just trying to get this by itself. What do I have to do first? Minus 3 on both sides. That's easy. We can do that. So I subtract 3 from both sides. I end up with -1. What next? Divide by 2. So I have cosine of x equal to -1 over 2. And voila, we have cosine of x isolated. That was our first step, to get cosine of x isolated. And now we need to think here. What two angle measurements would be equal to negative 1/2? It is the 3's, so cosine of pi over 3 is positive 1/2. So if we want negative 2 pi over 3, because it's cosine, yes. And then what other angle? 4 pi over 3. That's the quadrant 2 and the quadrant 3 versions of pi over 3, because cosine is negative in those two quadrants. Fabulous. Now, after this, in every other problem we've done today, we've written the general solutions. But in this problem, we have this domain restriction. And since I'm only going to answer angles between 0 and 2 pi, I don't want to include every revolution afterwards. So this little bit right here is telling me that we do not actually want or need a general solution. So instead of answering with a general solution with the plus 2 pi k, I only want these two angles. So x, are we using x or theta? X would be equal to 2 pi over 3 and 4 pi over 3. And that's it. I know that if we revolved this unit circle again, we'd hit these coterminal angles, but it said to only answer between 0 and 2 pi. So this domain restriction keeps me from doing the general solution. I just have a smaller list of numbers. Did we hold on to that? Do we feel okay? Because those have been the easy ones. These equations that we've been working with have been linear in form, right? They are kind of worked up to this point like a linear equation, as if we were solving for x in Algebra 1 class. But let's kick it up a notch, and let's start squaring some things. So we're going to need to bring back the ways that we solved quadratics. What were ways that we solved quadratics? Factoring. What else? How do you get rid of a square? Square roots. We may have to do just some like GCF moments. But if you remember, when you have higher order trigonometric functions, meaning you see squares and cubes, you're going to have to go back to the things we learned in Unit 2 and Unit 1, that's polynomials, about solving quadratics. If we wanted to square the variable x, it's very straightforward. We say x squared, easy peasy. But if we wanted to square the expression sine of x, we have to make sure we're writing it correctly. Because if you just do this, everybody look up at the board. If you write sine of x squared, that means you're squaring the variable x and not the entire expression sine of x. So we have to include parentheses around the entire thing and square it. But that's super annoying. So we made up a new notation for this. And if you are squaring a sine value or raising sine to any power, you put the power behind the letters. So this would be sine to the n power or sine squared. That is where you put the square. If you put it anywhere else, it's wrong. We're going to solve equations this way, but now they're quadratic in form. In fact, we'll get to some quadratic form, which is the whole thing. We'll get there. Okay, the function g is given by g of x equal to 3 minus 4 sine squared of x. What are the zeros of g on the interval from 0 to 2 pi? Couple things to note for yourself. We have a domain restriction. So are we going to write a general solution? No, we're just going to give actual 1 or 2 answers. Second thing to remember is this asks for the zeros. Mathematically, what does that mean I'm going to set my equation equal to? Great. All right, so let's do that. If we find the zeros of g, that means we're doing g of x equal to 0. So if I write that down, so we have 3 minus 4 sine squared of x equal to 0. We solve like normal, pretending it's a cute little quadratic. We want to isolate the term that's squared. We want to isolate the sine term. So I would subtract 3 from both sides. Negative 4 sine squared of x equal to negative 3. And what would I do next? Divide by negative 4. The negatives cancel out. I just get 3 over 4. So the sine is isolated, sort of. It's the only thing on its side, but it's currently squared. How do you get rid of a square? So if I square root both sides, I'm going to end up with sine of x equal to plus or minus the square root of 3 over 4. make sure you put the plus or minus when you are doing the square root. Now at this point, sine is isolated. We need to think about units or angles around our unit circle that would return square root 3 over 4. Oof, but I don't recognize that number from my unit circle. So instead, remember with square roots, you can take the square root of the top, which is square root 3, and the square root of the bottom, which is 2, separate. Square roots can go top and bottom. Square root of 4 is 2. Yeah. So question, if we're thinking about our unit circle, what are all of the angles that would return either positive or negative square root 3 over 2? So if you're using the hand trick, that means I want 3 fingers beneath my angle. 1, 2, 3. So that means I'm putting this finger down. What angle is that? Pi over 3. So that's the one that's positive. What other angle would give me positive? 2 pi over 3. But I can also include the negatives because it said plus or minus. 4 pi over 3, and then one more. 5 pi over 3. Because I can use both positive and negatives, we know all 4 of these angles return either the positive or negative version of square root 3 over 2. We have our solutions. And I didn't have to write 4 general form equations, which I might have to eventually, because it only asked me to do this between 0 and 2 pi. None of the other coterminal angles did we want. Did we follow, this is really the only new step. Did we follow this step? We know how to solve quadratics. The inverse of squaring is square rooting. We solve like normal. Example 7. Let's take it up a notch. It says, what are all values of theta for between 0 and 2 pi? So we're not writing general solutions here again. Even though it said the word all, the domain restriction takes over. We're just going to answer with some angles. Where cosine squared of theta is equal to negative cosine of theta. All right, let's get this one started. We have cosine squared of theta equal to negative cosine of theta. Don't write this down, but just look for a second. If I wrote this without the cosines and just used x's instead, it'd be x squared equal to negative x. And if you were solving this as a quadratic, what do you always set quadratics equal to solve? 0. So I would have added the x to the other side, yes? I'm going to do that same idea, but with the cosine. I'm going to add the cosine to the other side so that this is now set equal to 0. Okay, again, well, I guess you could write it down if you want to see the algebra version, which is x's. If we were doing this, and again, we have x squared plus x equal to 0, what would you do to solve this? Factor. What do x squared and x have in common? What do cosine squared and cosine have in common? Cosine. So I'm going to factor out a cosine. Cosine of theta goes outside a set of parentheses. I'm left with cosine, not squared, cosine of theta plus 1. In the same way, this would be x times x plus 1. Do we follow all of that? Okay. When you were doing this type of math, after you factored it and set it equal to 0, what would you do with each of those individual factors? Set them equal to 0. So I'm going to take cosine of theta, set it equal to 0, and I'm going to take cosine theta plus 1 and equal it to 0. At this point, now I don't have any more squares, and I have 2 little equations I can solve. Okay, what are the angles that would make cosine equal to 0? Pi over 2 and 3 pi over 2. That's horizontal displacement, so we are not far away from the y-axis at pi over 2 and 3 pi over 2. And if I solve the second one, I do actually have to do a little bit of solving because I need it to be isolated. So I'm going to move the negative 1 to the other side, or positive 1 becomes negative 1. And what is the angle measurement that would give me negative 1 for cosine? Pi. And since we don't want general solutions and we only want our answers to be on basically the first revolution of the circle between 0 and 2 pi, all we have to do is list out these angles. I have a habit of writing them in number order. It's a list, so you don't have to put them in number order necessarily, but I like it. Can't help myself. Well, let's back up because I know we're going to have questions. If you think of this as a regular quadratic question, it's a trigonometric equation that's a quadratic form. We can just set it equal to 0, like a quadratic, factor out the GCF, like a quadratic, set both factors equal to 0, like a quadratic, and solve each equation individually, like a quadratic. This is why we learn this after we do polynomials, because you need all of those skills to be able to solve trig equations. Can we try another one? And by we, I mean you. I think we're ready. A lot of the same skills we did in number 7, you're going to use for number 8. Okay, just to read it for you once, it says let f of x equal to 2 sine squared of x and g of x equal to square root 3 sine of x. In the xy plane, what are the x coordinates of the points of intersection? Equal, we're going to equal them to each other. Of the graph of f and g between 0 and 2 pi. So are you going to need to write a general solution? No. I want you to try this one. You've got people around you to ask questions to. Let's give it a shot. So at this point, we're either stuck or we got it. So let's go over it. I got you. If we're looking for the intersection point, that means we're looking for where f of x and g of x are equal. So if I solve this equation, that would be 2 sine squared of x equal to square root 3 sine of x. Now again, because I see that sine is squared, I have to think about my tools for solving quadratics, which would be to set it equal to 0, factor, and solve. So if I set this equal to 0, 2 sine of x minus square root 3 sine of x is going to be equal to 0. Now, just like we asked ourselves with quadratics, what do these two terms have in common? These two terms have a sine of x in common. I'm only going to take out sine of x, which means I'm left over with 2 sine of x minus square root 3. Right?
Wait, did you put the exponent in front of the 2? I mean, in front of the sign?
Did I put... No, though there was already a 2 there.
What do you do with the exponent then?
Oh, well, if you had this, and I took out an x, wouldn't this become 1? You would lower the degree by 1.
Okay.
So that's exactly what I did here. This was squared, but I took one of the signs out. If I multiplied this back, sine times sine is sine squared. So I haven't changed it at all. I've just written it in a different way. Okay? So we're here. Now we set each of these two tiny equations equal to 0. Did we get here?
Yes.
Fabulous. Then we have to think to ourselves, what are the angles that would give me 0 for sine? Well, that's 0 and pi. And then for this other one, I still have to isolate the sine term. So I'm going to add square root 3 to the other side. Oops, I missed the x here. And then divide by 2. So this is sine of x equal to square root 3 over 2. The two angles that would give me square root 3 over 2 for sine, positive, are pi over 3 and 2 pi over 3. Which means that the 4 solutions to this equation in one rotation of the unit circle, so between 0 and 2 pi, are x equal to, and again, I can't help myself, I'm going to put them in number order. You don't have to put them in number order. You just have to make sure they're all in your list. We can also solve trig inequalities. Part of this is very easy and part of this is pretty challenging. The first part's very easy. In Unit 1, we solved inequalities for polynomials and rationals. We did it graphically by just looking what is above or below the number, in this case 0. So on the graph of f, this is example 9, the graph of f is defined for negative 2 pi and 2 pi. That's my domain restriction. So if you notice, it starts at negative 2 pi and it ends at 2 pi. We're only looking between these two numbers. Okay. What are the values of x for which f of x is less than or equal to 0? Well, let's see. The places where this function is less than or equal to 0 will be all of the places where it is equal to or below the x-axis. My pen overwrote it. I'll put it back in a second. Bless you. Oops. Okay. Now, we just need to create an interval notation that tells me all of these places. So where is the first place that this is equal to 0? Negative 2 pi. But there's nothing else except for that number. So I'm going to use the set notation of negative 2 pi. Then I'm going to have another place. What is the next place that this is less than or equal to 0? Negative pi to 0 with the bracket because we are equal to it. And then the last one, obviously, you can see is from pi to 2 pi. That's how you answer inequalities. From a graph? Pretty simple. Yes?
No.
What's the no for? Can I help?
Like, how do you get all of that?
Well, look at the graph. Where is it actually below? This is 0.
Oh.
So where is it actually below 0? From here to here, from here to here, and at this place right here. Yeah.
Oh, no, mind.
If we're trying to solve these analytically, basically with a unit circle, meaning we don't have a graph, the thought process changes on how you answer an inequality. So example 10 says, what are the values of theta between 0 and 2 pi? So we do have a little domain restriction, so one circle, right? For which sine of theta is greater than or equal to square root 2 over 2. What's up?
Is this on Khan Academy?
It probably, I don't know if the AP version of it is yet because it's still a new course, but you can always check. So sine of theta greater than or equal to square root of 2 over 2. Right now, and I put this unit circle here for a reason, I want you to take your pink highlighter and I want you to highlight the two places on this unit circle where sine is equal to positive square root 2 over 2. I want you to highlight those two coordinates.
This is my song.
I see one of them here, and I see one of them here. Are those the ones you found? Yes. So we want the values of theta for which the ratio for sine is bigger than this. And since sine is a vertical displacement, that means we want the angles that are above or bigger than these two angles. We want all of that. So what we're going to do is we're going to use an interval that goes from pi over 4 all the way to 3 pi over 4. Because all of the angles in between that are vertically displaced higher than square root 2 over 2. So the solution here is from pi over 4 to 3 pi over 4. Okay. Number 11 says let f of x equal to 4 plus 2 cosine of x and let g of x equal to 3. What are all the values in the xy plane between 0 and 2 pi? Again, that's my little domain restriction, so one rotation. For which f of x is less than g of x. Okay, they're going to make us work here a little bit. So if we have f of x less than g of x, that means 4 plus 2 times the cosine of x has to be less than 3. Okay, before I can even look at this unit circle, I got to isolate the trig function. I'm going to subtract 4 from both sides, and I'm going to divide by 2. So I'm trying to figure out where this graph is where the cosine coordinate is less than negative 1/2. So on the same unit circle and with blue, I want you to highlight the two coordinate points that are giving you negative 1/2 for cosine. You're welcome. There should be two places. It should be here and here. Did we find those two places? So if we want our horizontal displacement, cosine, to be smaller than negative 1/2, that means we want it to be to the left of these two coordinates. So what we're going to do is we're going to go in between this angle, and we're going to include everything that's smaller than that with my horizontal displacement, which means we're going to include everything between 2 pi over 3 and 4 pi over 3. Now, because this question, the inequality does not have the or equal to line underneath the symbol, should I use brackets or parentheses? Fabulous. So this answer is going to be from 2 pi over 3 to 4 pi over 3. We following? Okay. Example 12. We're still going to use that unit circle. I just have to zoom down a little bit. Let h of x equal to 3 cosine of x and let k of x equal to square root 3 plus cosine of x. What are all the values of x in the xy plane between 0 and 2 pi for which h of x is greater than k of x? Okay, we're wanting to solve this inequality, so we set it up the way we had been working. We're going to do h of x greater than k of x. H of x is 3 cosine of x, and k of x is square root 3 plus cosine of x. Before we pause and panic, are there any squared terms here? No, so I can use linear ideas to solve this equation, which means I want to put all of the cosines on the same side. How do you get this cosine onto the other side? Subtract it. So I have 3 cosine of x minus cosine of x, which is how many cosines of x? 2. So we have 2 cosine of x greater than square root 3. What do we divide by? 2. So we're looking for where cosine of x is greater than square root 3 over 2. Cool beans. That's what I'm going to try to highlight or look at on my unit circle. So let's find all the places on our unit circle where cosine is greater than square root 3 over 2. Or that it's equal to positive square root 3 over 2. I see 2 places. It would be here and here. Do you agree? Okay, but I'm going to highlight this one specifically, so follow my highlighting. Remember, we are going from 0 to pi over 2. I'm sorry, to 2 pi, which means I need to start my highlighting not at 11 pi over 6, but I need to start my highlighting right here. Put a little dot right there, and now go up to pi over 6. And then we have a whole section of our unit circle we are not including as we circle around. And then boom, I pick it back up at 11 pi over 6. So we are going to have 2 intervals here from 0 to pi over 6 and then from 11 pi over 6 to 2 pi. Because we're going counterclockwise around our unit circle, we can't say we start at 11 pi over 6 and go to pi over 6. That doesn't make sense. We have to start at a smaller number, which means our solution here is from 0 to pi over 6, union 11 pi over 6, comma 2 pi. Now I'll tell you, when you do your CYUs today, there's a couple questions that have tangent. If you can't figure out the tangent ones because they're kind of crazy, come in and ask me questions. I will help you with them, but I want you to try them on your own first. See if you can draw some good conclusions with tangent.